Okay, so this video is going to be a tale of two integrals. Well, I suppose it's going to be a tale of the same integral, but we're going to look at that integral in two different ways. Now, you know what an integral does. It looks at the area under the curve. In particular, when you have bounds, a definite integral with bounds here. We've got bounds of 1 and 2, and well, that's going to give you the area under this function. Now, does this function look exactly like what I've drawn? You know, of course not, probably, frankly, but you know, this is the idea. We're trying to compute the area under the function between 1 and 2. And we know how this is done, because if you want to compute the area between 1 and 2 of your function, then you just need capital F of 2 minus capital F of 1 fundamental theorem. So the first challenge here is going to be to compute the antiderivative, and then upon finding the antiderivative function, plug in 2, plug in 1, problem solved. Okay, so let's try to find the antiderivative here. But one of the challenges that shows up whenever you try to find the antiderivative is that this is not a cookie cutter situation, and we'd have to use substitution to pull it off. Because you can see that there are 2 bits being multiplied, which is what pops out of the chain rule, f prime u times u prime. So I'll tell you what, let me just write that out. So you get the multiplication that shows up as a result of the chain rule, and you also get 2 bits of your expression that are related by derivative. So you've done a number of these in exercises to this point. So let's set u equal to the x cubed in order that, take derivative, du, 3x squared dx. Now, of course, 3x squared dx is not exactly what's in our function. We've got an x squared dx, but that's cool because we can make x squared dx if we just take this expression and multiply it by a third. So multiply it by a third, we'll have exactly x squared dx, and then we can replace x squared dx with a third du, and we won't be altering things a bit. So the long story short is we are then, to find the antiderivative function, simply integrating. Let's see, we have 1/3 du from our x squared dx. I'll factor out the 1/3 because you know any constant multiple can be factored out of an integral. And then with the 1/3 du swapped in for the x squared dx, all we have left is to deal with the x cubed plus 7 squared, but that would be just u squared. And then whenever we take this integral, let's see, the integral of u squared is going to be 1/3 u to the third plus c by necessity. And I guess long story short, when you have the third that's on the outside times the third that would be from the antiderivative of u squared, you're going to get 1/9 u cubed plus c. But of course, that's not the antiderivative function. Technically, the antiderivative function would have to be in terms of x. So the antiderivative function would be 1/9 x cubed plus 7 cubed plus c. Okay, so now we've computed the antiderivative. But that's only part of the problem, right? Because now we have to plug in 2 and plug in 1. So we've got the antiderivative function, and now we plug in 2, we plug in 1, and I tell you what, I don't love the fact that this is going to get a little bit ugly, but it is what it is, that's fine. 1/9 times, I'm going to plug in 2, so I have 2 cubed plus 7 cubed minus 1/9 times 1 cubed plus 7 cubed. If I run the numbers on that, this is 8 plus 7, that's 15. 15 cubed is huge. I'm not even going to crunch that number. 1 plus 7, that's 8 cubed. This is what it is. But the long story short is that is the area. I mean, I guess technically, if you were giving this on a test, you're probably not going to want to leave it like that. So you probably compute the numbers, and whatever the number turns out to be is whatever the number turns out to be, and we have it. Okay, and the long story short is, how did we go about that process? Well, we wanted to find the area under the curve, so we needed to know the antiderivative function. We worked through the computation to get the antiderivative function, and once we had the antiderivative function, it was merely a matter of plugging and chugging. By the way, the c dropped off here, right, because whatever you chose c to be would subtract whenever you do f of 2 minus f of 1, the c's would drop off, and well, you'd ultimately boil down to this. Now, that was a lot of work, actually. That took a lot of time to articulate and talk through. But here's what I want to sort of implore from you and to think in terms of. Because whenever you're computing just an antiderivative and you're using substitution, you've always got to go back to x in order to phrase it in terms of the original problem. But whenever you're computing the area under the curve, I claim there's a shortcut around having to communicate back into the language of x. And we can actually exploit the language of u in order to compute the integral. So, I tell you what, this video's gone a little while. Let me cut the video here. I'll come back and do this next, like the tale of two integrals here, and let's compute the same integral with a different method, and let's just compare the times, see how long it takes.